For the physical properties of aldehydes and ketones, we care about two types of physical properties, the solubility and the boiling point. Okay, so the rule says that, and this is the general rule that we go with all functional groups, up to 5 carbons in there, up to 5 carbons or lower. So our cutoff is 5 carbons. Aldehydes and ketones are water soluble. So aldehydes and ketones are water soluble. The solubility, The solubility of the aldehydes and ketones, it depends on hydrogen bonding. So that solubility here depends on H bonding. And of course, when we talk about solubility, you have to check what solvent you are dissolving the aldehyde and ketone with, and to check if that solvent has hydrogen bonding with the aldehyde or the ketone. So if it does, and your aldehyde and ketone are no more than 5 carbons, then your aldehydes and ketones are going to be soluble in that solvent. Please remember that as the number of carbons increase, as the solubility is going to decrease. Okay? With respect to the boiling point, on the other hand, not just the hydrogen bonding affects the boiling point, it's other intermolecular forces as well. So that is a revision of the first part of the course, which is Chem 111. I believe that you went over intermolecular forces. I'm just going to call them IM in there. And there are different types of intermolecular forces between molecules. And these are forces that happen when you have these molecules that are next to each other. So for the intermolecular forces, what do I have? I have the weakest type of intermolecular force, which we call the London forces. And these London forces, they exist between nonpolar compounds, meaning that compounds that have a long carbon chain. And here I do have long carbon chains in there for the aldehydes and for the ketones. So if you bring them next to each other, you will create that fake interaction between them, but it's going to be very, very weak in there. We call them van der Waals forces or London forces. So the van der Waals forces or the London forces, and these, they exist between compounds that contain a carbon chain. So any carbon chain compounds in there. This means that every single organic compound, if it has a carbon chain, then it will have London forces. Let's say if I'm talking about propanol, butanol, pentanol, pentanone, hexanone, all of those, they do have London forces when they are brought next to each other. Okay, this is the weakest type of intermolecular force, and it exists between non-polar carbon chains. The second type of intermolecular force is the dipole-dipole interaction. So the dipole-dipole interaction. Now, that dipole-dipole interaction normally exists when the functional group has an electronegative element. Okay, and these types of intermolecular forces, they are stronger than the London forces, way stronger than the London forces. They are not very strong, but they are stronger than the London forces. What do I mean by dipole-dipole? Let's say, for example, if I have a functional group that has a difference in electronegativity, this means that I need to have an electronegative element in the functional group, like alcohols, like aldehydes, like ketones. All of those, they contain oxygen. And if I look at the electronegativity trend in the periodic table, electronegativity increases from left to right in a period and bottom to top in the group. So if I am looking between the carbon and oxygen in there, within the carbonyl, I would see some difference in the electronegativity, where oxygen is more electronegative than carbon. So when oxygen is more electronegative, what will it do? Actually, it will take electrons from the carbon because it has more electrons, or it has the tendency to pull electrons from the carbon. This is the definition of electronegativity, the tendency of the element to pull electrons towards itself. So here in this case, my direction of polarization, which is the movement of electrons, is going to be towards the oxygen. That is going to create a dipole. And that dipole is represented by charges in there on the carbon and on the oxygen. So the oxygen, because it took electrons from the carbon, now it's fully charged. So I'm going to represent that gain of electrons by a negative charge, and the loss of electrons of the carbon by a plus charge. And this is called a dipole in there. So imagine like whenever I have all of these different or aldehydes, a lot of aldehydes or a lot of ketones, since they both contain the same carbonyl next to each other, what's going to happen? What's going to happen here is that they're going to arrange themselves in a way where all of them will have a dipole in there, and the negative charge will interact with the plus charge of the carbon. The negative charge of the oxygen will interact with the plus charge of the carbon, and so forth. Okay, and so forth. So the arrangement of the solution, it's going to be a dipole in there. So where's the dipole? The dipole is the fake interaction between the oxygen and the carbon. I'm creating an interaction in there, not a bond, it's an interaction because it's a solution of aldehydes. So a lot of aldehyde molecules in the same place in there. So these aldehyde molecules, they're going to make a dipole so that they are interacting with each other. So they're going to have a dipole between the negative and the positive, the dipole between the negative and the positive in here. And this is called a dipole-dipole interaction. When it exists whenever your functional group has difference in electronegativity. So you have carbons, you have oxygens in there, then you will have a dipole-dipole interaction. Same thing if you have an alcohol solution, same thing. So you have a COH in there, so the solution or the alcohol molecules will arrange themselves in a way also to have a dipole-dipole interaction. Alkanes don't have a dipole-dipole interaction, they only have London forces because they are all made up of carbons. So to have a dipole-dipole interaction, you need to have difference in electronegativity between the molecules in the compound. Okay, and that dipole-dipole interaction, it is stronger than the van der Waal forces in there. And if it exists, then the boiling point of the solution is going to be higher. Okay, so if I'm comparing a structure that only has London forces and another one that has dipole-dipole, then in this case, the one that has a dipole-dipole has a higher boiling point. Intermolecular forces, they do affect the boiling point of the structure. And then finally, we have the last type of intermolecular forces, which is the hydrogen bonding. The hydrogen bonding is the strongest type of intermolecular force. So this one is going to be the strongest type of intermolecular force, and normally the hydrogen bonding in there also affects the boiling point. So if you have a compound that makes hydrogen bonding, it's going to be the highest boiling point compared to the one that only does dipole-dipole interaction. Okay, so over here what I have is dipole-dipole interactions between the carbons and the oxygen. So here I do have a dipole interaction. Same thing between the oxygen and the carbon. I have another, I'm going to represent the dipole-dipole as DD. Okay, so because of the dipole-dipole interactions, we can say that carbonyls in there, they are considered to be slightly polar. So that is the polar compound in there. Why we are mentioning polarity? Polarity is the movement of electrons. So if you have electrons being moved between the carbon and the oxygen, then we say that this functional group is going to be slightly polar. Okay, so the question is, do aldehydes or ketone undergo hydrogen bonding with themselves? So in order to know this, when I say with themselves, then just go ahead and throw in two aldehyde molecules, put them next to each other, or two ketone molecules, put them next to each other, and check, do I have the condition of the hydrogen bonding satisfied? So in the hydrogen bonding condition is whenever I have a hydrogen connected with an electronegative element, and that hydrogen needs to interact with an electronegative element. The electronegative element is either oxygen, nitrogen, or fluorine. Same thing in there, oxygen, nitrogen, or fluorine in there. So do I have this? No. To start with, I do have an electronegative element, which is the oxygen, yes, but I don't have a hydrogen connected to O in there. I do have a hydrogen connected to a carbon. So here in this case, I would say that there is no hydrogen bonding. So if there is no hydrogen bonding, what does this tell me about the boiling point of the aldehydes? This means that the boiling point of the aldehyde is not very high because there is no hydrogen bonding. But please pay attention that aldehydes has other intermolecular forces going on other than the hydrogen bonding. And these intermolecular forces, the dipole, and the hydrogen bonding, both they affect the boiling point. Although the hydrogen bonding is the strongest, and the presence of the hydrogen bonding will make the boiling point shoot high, but the dipole interaction as well increases the boiling point. So aldehydes, they have no hydrogen bonding, but the aldehydes does have a dipole interaction in there. So you do have a dipole interaction, and that interaction is going to be between, this is negative, this is positive. So you do have a dipole interaction between the oxygen and the carbon in there, and that is going to increase slightly the boiling point of the aldehyde. So let's say, for example, or the ketone. So let's say, for example, if I gave you a chain of 5 carbons of alkane and a chain of 5 carbons of ketone, and I ask you this, which one has a higher boiling point? Then go with this rule, okay? Then go with this rule in there. And the rule says that the one with the most intermolecular forces, so the more the intermolecular forces implies the higher is the boiling point. So let's agree over here that the London forces always exists with any carbon chain. So if you look at your structure and see that it has a carbon chain, this one has a carbon chain on these two ends in there, then both of them will have London forces, which I'm going to go ahead and represent this as the van der Waals forces. So both, they do have van der Waals forces in there. Okay, now alkanes only have van der Waals forces, which are London forces. These are the weakest. They don't have any dipole or hydrogen bonding. On the other hand, ketones, they do have dipole interaction. And because the ketones here have two types of intermolecular forces, and the dipole is slightly higher in intermolecular force interaction than the van der Waals, then I would say that ketones in there, because of the presence of the dipole interaction, ketones, they do have higher boiling point. So ketones, they have higher boiling point because they have more intermolecular forces, or they have stronger intermolecular forces. The dipole interaction is stronger than the van der Waals interaction in there. Okay. That is regarding the comparison in there. I know that there is no hydrogen bonding between ketones. There's no hydrogen bonding between aldehydes in there. So this is why the boiling point of the ketones and the aldehydes is not as high as that of the alcohol. So let's say, for example, if I have something like this, if I have an alkane now, let's include the alcohol and the aldehyde. And I'll ask you, okay, arrange those from the highest to the lowest boiling point. Then what you need to do is figure out the intermolecular forces for each one. So this one has the van der Waals force. This one, we've talked about it in the previous chapter, and we said that it does have, of course, long carbon chain, which is a 3-carbon, not long, but it's a 3-carbon chain. It does have van der Waals in there. It does have a dipole, and it has hydrogen bonding as well. So see, it has all of these 3 intermolecular forces. The more the intermolecular forces, the higher is the boiling point. Aldehydes have only van der Waals forces and have dipole. Now we can go ahead and arrange those from the highest to the lowest boiling point in there. And you would say that alcohols, they are the highest boiling point. So the alcohol is the highest boiling point in there versus the aldehydes, which have 2 types of intermolecular forces, versus the alkane in there. The alkane is the 3 carbons versus the alkane. Alkane has the lowest boiling point. So this one is going to have the lowest boiling point, and this one is going to have the highest boiling point. Guys, whenever you are working with alcohols and dipole interactions, as we did for the aldehydes, exactly do the same. So we're going to put the 2 molecules of alcohols next to each other. Doesn't matter the R chain. The R chain is already there, okay? So put 2 molecules of alcohols that are next to each other in there and see if there's any dipole interaction. Now, I know for every alcohol, I have the oxygen and the OH in there. And there is a difference in the direction of polarization. So the oxygen will take electrons away from the hydrogen and they create a partial positive and a partial negative. I need to know my charges for every single molecule of the alcohol so that when I arrange them next to each other, I can create a dipole where the positive and the negative charge, they interact with each other. Okay, again, this one is a negative, this one is a positive in there. So whenever I am creating again, this one is the direction of polarization. So whenever I'm putting them next to each other, then I will have a dipole between the positive charge hydrogen and the negative charge oxygen in there. And this is how they are arranged. They are arranged in the solution. Just think of, you have a solution of alcohol molecules. How are they going to be with respect to each other? Always they are positioned in a way that the dipole positive charge interacts with the dipole negative charge of the next molecule in there, and so forth. Okay, so that is regarding the alcohol dipole interaction. Also, alcohols, they do have hydrogen bonding because they contain a hydrogen connected with an electronegative element, and that can bond with another electronegative element. So now if I want to go ahead and compare aldehydes and ketones and their boiling point. So we've talked about aldehydes alone, ketones alone. And we said that aldehydes and ketones, they have no hydrogen bonding whatsoever with each other. Okay. Now, if I want to compare aldehydes and ketones, which one has a higher boiling point? It's always my cutoff is always 5 carbons. And always ketones, they have higher boiling points than aldehydes in there. And always, this is going to be my cutoff. So up to 5 carbons, ketones, they have higher boiling point than aldehydes. Now, as the number of carbons increase, then this means that I need to go with the aldehydes. Aldehydes will have a higher boiling point than the ketone. Okay, now with respect to the solubility of the aldehydes and ketones in water, when I talk about solubility, I need to know the solvent that I'm working with so that I can check and see if there is any hydrogen bonding in there. So the question is, let's say, for example, I'm picking ethanol, and the question is ethanol water soluble? Is ethanol soluble in methanol? So I am checking the solubility for both here. So I'm going to check the solubility. Solubility has to do with hydrogen bonding. Pay attention. Boiling point has to do with intermolecular forces. the higher the or the more the intermolecular forces, the higher is the boiling point. But solubility, we care about hydrogen bonding in there, especially when we are working with aqueous solutions, with aqueous solvents like water, like methanol. They are water soluble. They dissolve in water. So this is why we care about the hydrogen bonding here. So any solubility question, please check hydrogen bonding. Okay, so we're going to have ethanol in there. Do I have any hydrogen bonding with water? Well, yes, because I do have the condition where I have a hydrogen here connected to an electronegative element, which is the oxygen, and that hydrogen interacts with an electronegative element, which is the carbonyl. So yes, I do have here hydrogen bonding between the aldehyde and the water. My aldehyde is less than 5 carbons, then yes, it is water soluble. It is water soluble. Let's have another example. That same aldehyde. Is it soluble in methanol? So check hydrogen bonding again and see. I do have a hydrogen connected to an electronegative element here. So this is the hydrogen connected to the electronegative element. And this hydrogen and this hydrogen interacts with the carbonyl electronegative element. So I do have hydrogen bonding here in there between the hydrogen and the oxygen. And my aldehyde is less than 5 carbons. This is very important to check, because if it is more, then the solubility is going to decrease. So pay attention to that. And as I increase the number of carbons, your aldehydes are now going to be water soluble. Same thing as ketones. So here, yes, it is water soluble. Okay, please guys remember that more than 5 carbons in there, the solubility is going to decrease. So to be water soluble, you need to have less than or equal to 5 carbons and hydrogen bonding exists. Same thing for ketones, same idea in there. I do have hydrogen bonding in here, so yes, the ketone is water soluble. That is water soluble. Same thing over here. Ketones and methanols, I do have hydrogen bonding in there. So yes, the ketones are water soluble as well.